There is a star in our galaxy that once seemed to be older than the universe itself. Not older than Earth, not older than the Sun, older than the universe. If that sentence were literally true, it would be a fatal crack in cosmology. It would mean the Big Bang timeline is wrong, the expansion history is wrong, and the way we read the sky is broken at the most basic level. And yet the star is real. You can point a telescope toward the constellation Libra and measure its light. It has a name, but astronomers gave it a nickname that sounds like a myth: the Methuselah star. Here's the mystery. How can anything in the universe be older than the universe? The answer is not time travel, and it's not the Big Bang didn't happen. The real answer is much more unsettling and much more useful. Sometimes a single object can expose every fragile assumption in the way we measure reality. Because when you try to date a star, you're not reading a birth certificate. You're solving a cosmic puzzle with missing pieces, and you only see the final picture if your measurements, your physics, and your models all agree. And in this case, for a while, they didn't. The star is called HD 40283. It's relatively close by cosmic standards, about a few hundred light-years away, so close that its motion across the sky is obvious even in old data. It's also visibly ancient in a way astronomers can recognize instantly. It's dimmer and more evolved than a normal star like the Sun, and its chemical fingerprint is extremely metal-poor. In astronomy, metals means everything heavier than helium. Carbon, oxygen, silicon, iron, those are metals in the astronomical sense. And here's why that matters. The early universe was basically hydrogen and helium with a tiny sprinkle of lithium. That's it. The heavier elements were forged later, inside stars, and then scattered by supernovae. So the oldest stars should be metal-poor because they formed before the universe had time to enrich itself with heavy elements. HD 1408283 is one of those ancient survivors. It formed when the Milky Way was young and the universe was still in its first chapters. It's a relic from a time when there were no rocky planets, no oxygen-rich atmospheres, no chemistry that looks like home. So astronomers set out to do a simple thing: estimate its age. And what they got at one point was around 14.5 billion years. But the universe is about 13.8 billion years old. That's not a little off, that's impossible. So either the star was lying, or we were. To understand how this can happen, you need to know what age of a star even means. You can't watch a star evolve in real time. Stars change over millions and billions of years. So instead of watching one star grow old, we compare many stars at different life stages, then use physics to build a timeline. At the center of that timeline is a simple engine: nuclear fusion. A star shines because it's converting mass into energy. In its core, hydrogen nuclei fuse into helium. That process releases energy, which pushes outward as radiation and pressure. Gravity pushes inward. A star is basically a long-term battle between pressure trying to expand it and gravity trying to crush it. As long as the core has hydrogen to burn, the star sits in a stable phase called the main sequence. The Sun is there right now. But eventually, the hydrogen in the core runs low. The star's core contracts, heats up, and fusion changes location and intensity. The star evolves off the main sequence into later stages. That evolution leaves a fingerprint in the star's brightness and temperature. In other words, a star's color and luminosity tell you where it is in its life cycle. And that's how astronomers estimate age. They take a star's temperature and luminosity, compare it to stellar evolution models, and find the point on the model timeline that matches. If you've ever seen a heart-sprung Russell diagram, where stars are plotted by brightness and temperature, that diagram is a map of stellar lives. Young, stable stars sit in one region. Older, evolved stars peel away into another. The moment a star begins leaving the main sequence is particularly useful because that turn-off is strongly tied to age. HD 1140283 is near that evolutionary turn-off. It's in a late stage for a star of its mass. And because it's metal-poor, its evolution is different from a metal-rich star like the Sun. That last part is the key. Metallicity affects how energy moves through the star. Heavy elements change opacity, how easily radiation escapes. They change the efficiency of energy transport. They change the exact temperatures and pressures in the core. And those changes can shift the predicted age by huge amounts. So the age you infer is only as good as your understanding of the star's chemistry and physics. But there's an even more brutal dependency: distance. Because to know a star's luminosity, you need to know how far away it is. A star looks dim for two reasons. Either it is actually dim, or it's very far away. If you misjudge distance, you misjudge true brightness. And if you misjudge brightness, you misjudge where it sits on the timeline. And if you misjudge that, you misjudge age. So how do we measure distance to a star? We use parallax. Parallax is the shift in a nearby object's apparent position as you move your viewpoint. Hold up a finger and close one eye, then the other. Your finger jumps relative to the background. That jump is parallax. For stars, we use Earth's orbit. Measure a star's position against distant background stars, then measure it again 6 months later from the opposite side of the orbit. The star appears to shift by a tiny angle. That angle tells you distance. The problem is that the angles are unbelievably small. Even for relatively nearby stars, the shift is measured in fractions of arcseconds. Angles so tiny you could cover them with a coin from thousands of kilometers away. So even a small measurement error in parallax can translate into a significant distance error. And a distance error becomes a luminosity error. And luminosity errors become age errors. For HD 1140283, the distance was measured using precise space telescopes and later with improved data. But for a time, the uncertainty was large enough that the inferred luminosity could slide around. And when it slid, the age slid with it. That's how you can get a number that's older than the universe without breaking physics. You don't need a huge mistake. You need a small uncertainty in distance, combined with uncertainties in stellar models, combined with the star's unusual chemistry. In other words, the universe isn't telling you, "I'm older than myself." It's telling you, your measurement has a margin and you're standing right on the edge of it. But the mystery doesn't end there. Because even with uncertainty, the result was uncomfortably close. Not way too old, but just slightly too old. That's what made it terrifying. If HD 1140283 had come out as 30 billion years old, everyone would laugh and immediately point to a broken input. But 14.5 versus 13.8 is dangerously believable. It's close enough to suggest the star might be fine, and our cosmology might be the thing on trial. So scientists did what science does when it meets a paradox. They hunted the weak links. They questioned the distance first. They reanalyzed the parallax. They improved calibration. They updated the star's luminosity. Then they questioned the star's composition. Spectroscopy, splitting starlight into a rainbow, reveals absorption lines that correspond to different elements. Those lines let you estimate metallicity. But that estimation depends on modeling the star's atmosphere, temperature gradients, and how lines form under conditions far from a lab. They refined those models. They updated the chemical abundances. Then they questioned the internal physics used in stellar evolution models. One of the subtle villains here is oxygen. In very old, metal-poor stars, the exact amount of oxygen relative to iron changes the star's opacity and fusion efficiency, which changes its evolutionary track, and therefore its age estimate. Another villain is how energy is transported in the star's outer layers. Convection. Convection is messy. It's turbulent fluid flow, not a clean equation. Models approximate it. Small changes in how convection is treated can shift the predicted temperature and luminosity over time. Another villain is nuclear reaction rates. Fusion doesn't happen at the same rate under all conditions. The exact reaction rates, how often protons fuse, how fast helium builds, matter. Physicists measure these rates in experiments and infer them for stellar conditions, but uncertainties remain. Then there's diffusion and settling. Over billions of years, heavier elements can slowly sink within a star, changing the surface composition we observe. If you assume today's surface composition equals the star's original composition, you can misread the star's history. So the star became a stress test. Every tiny assumption was forced into the spotlight, and over time, the numbers moved. With improved distance measurements and refined models, the age estimate for HD 114-283 shifted downward. Instead of 14.5 billion years, it landed closer to about 14 billion, and then, with uncertainties, it became compatible with the universe's age. Not comfortably compatible. Compatible in the way a tightrope is compatible with gravity. The updated estimate can be thought HD 114-283 likely formed very early, perhaps within a few 100 million years after the Big Bang. That makes it one of the oldest known stars in the Milky Way. It is ancient beyond intuition, but it is not older than the universe. The paradox dissolves into error bars. So is that the end? Just measurement error? Not at all. Because this star's near-impossible age taught us something profound. Our cosmological age estimate and our stellar age estimates are independent clocks. One clock is the expansion history of the universe, inferred from the cosmic microwave background and the behavior of galaxies. The other clock is nuclear physics inside stars. When those clocks agree, it's not just a nice coincidence. It's a deep consistency check on physics across completely different scales. It means the same universe is being described correctly by both relativity and quantum nuclear processes. When a star nearly contradicts the age of the universe, it doesn't mean the star is wrong. It means we are probing the boundary of what we know. And that boundary is where discoveries happen. Because to resolve the paradox, scientists had to make everything more precise. Parallax measurements, stellar atmospheres, reaction rates, diffusion models. Every refinement made stellar astrophysics stronger. Now step back and realize what an age estimate really is. It's not a single number. It's a probability distribution. It's a range of possible ages given uncertainties. That's the difference between a clickbait paradox and real science. Science isn't afraid of uncertainty. It quantifies it. But the emotional part of this story is still worth feeling. When you hear older than the universe, your mind wants a narrative twist, hidden time, alternate cosmology, pre-Big Bang objects. And those ideas aren't worthless. They're just not necessary here. The real twist is that the universe is so finely measurable now that a single star can challenge the cosmic timeline by less than 1 billion years, and we can argue about it with data. That's insane. Now, there's another layer. Why do we even know the age of the universe so precisely? We weren't born with that number. We inferred it from the afterglow of the Big Bang, the cosmic microwave background, a faint radiation filling space at about 2.7 Kelvin. That radiation carries tiny temperature variations across the sky, little ripples that are the frozen imprint of sound waves in the early universe. By measuring the pattern of those ripples, cosmologists can infer the universe's composition, how much matter, and dark energy exist, and how fast the universe expands. From that, they can infer an age. So the universe's age comes from a global fingerprint. The star's age comes from local physics. 2 clocks, 2 methods, 1 reality. When the star appeared older than the universe, it was like 2 watches disagreeing. That's how you know one, or both, needs calibration. And here's the core of the story. Calibration is the hidden science that keeps all of physics together. Most discoveries are not a sudden new idea. They are a slow sharpening of measurement until the universe can no longer hide behind fuzziness. Now let's make the story tangible. Suppose your distance estimate to a star is off by just a few percent. That might sound tiny, but luminosity scales with the square of distance. Double the distance and the luminosity looks 4 times bigger. So a small distance error changes luminosity enough to shift a star's position in the HR diagram, and that shift can correspond to billions of years when you are near the turn-off point. That's why HD 140283 is a perfect trap. It sits in a region where the age-luminosity relationship is steep. It's like trying to measure a mountain's height when you're standing on a cliff edge. One step changes everything. Now add metallicity uncertainty. Metal-poor stars have lower opacity, which lets energy escape more easily, affecting temperature and luminosity. That shifts the evolutionary track. If you slightly misestimate metallicity or oxygen abundance, you shift the track and you shift the inferred age. So the paradox is not a single problem. It's a pileup of small uncertainties that align in the same direction. And that's what made the headline "Older than the Universe" temporarily possible. But in the bigger picture, the Methuselah star is still extraordinary. It formed when the universe was young. That means it formed when the Milky Way was still assembling, when galaxies were smaller and more chaotic, when star formation was different, when the first supernovae had only begun to seed space with metals. So, how did it survive? Old stars can survive because low-mass stars burn fuel slowly. The Sun will live around 10 billion years. Stars slightly smaller than the Sun can live much longer, tens of billions of years. HD 140283 is in that low-mass regime. It has been quietly burning for almost the entire history of the cosmos. That alone is a kind of time travel. When we look at such a star, we're seeing a physical object that has persisted through almost everything that has ever happened since the first galaxies formed. It has watched galaxy collisions. It has watched the Milky Way grow. It has watched generations of stars live and die, enriching space with heavy elements. It has watched the raw universe become chemically complex. And it is still here, In a way, the Methuselah star is a bridge between cosmology and archaeology. It is the universe's oldest surviving artifact. So the title, Older Than the Universe, was wrong in the literal sense. But it captured the emotional truth. This star is so ancient that it forces you to rethink what old means. Now, there's a final twist you can appreciate once you understand the story. The fact that a star can almost appear older than the universe is actually evidence that we're doing something right. Because if our models were wildly wrong, the discrepancy wouldn't be subtle. It would be massive. The fact that it came down to a fraction of a billion years means our theories are close to reality. The disagreement lived in the uncertainties, not in the foundations. That's the best kind of contradiction, one that makes you improve. But you might wonder, what if the universe's age estimate changes in the future? Could this paradox come back? Yes, and that's the point. Physics is always provisional. The age of the universe depends on measured parameters like the Hubble constant, and there's still tension in measurements of that constant using different methods. Some measurements suggest a slightly different expansion rate. If the expansion history shifts, the inferred age can shift too. So stars like HD 1140283 remain important. They are independent age anchors. They help constrain cosmology. If cosmological models drift too far, ancient stars push back. And that is how you keep reality honest. Multiple independent methods checking each other. Now imagine a future where we find even older candidates, stars with even lower metallicity, formed even closer to the first generation. Some may be so primitive that they preserve chemical fingerprints of the earliest supernovae. Some may be so faint and old that we barely detect them. Every one of those stars is a time capsule. And every one of them is a chance to test our story of the universe. So here's the true ending. The Methuselah star does not overthrow the Big Bang. It does something better. It makes the Big Bang story stronger by forcing it to confront data at its limits. It reminds you that science isn't a list of facts. It's a living process of squeezing uncertainty until only reality remains. And it leaves you with a haunting thought. If a star can almost be older than the universe, it means we are now measuring time on scales that dwarf human imagination. We are not just asking, how old is this star? We are asking, how old is reality? And we can answer, within a fraction of a billion years. That is the kind of precision that turns the cosmos from myth into something you can interrogate. So the next time you look at the night sky, remember, some of those lights are not just distant. They are ancient witnesses. They formed when the universe was still learning how to make complexity. And one of them, one stubborn, metal-poor star, once forced us to ask the most impossible question imaginable. Can the universe be younger than one of its own stars? The answer is no. But the fact that we can even ask that question and chase it with numbers is one of the most extraordinary things the human species has ever done.